let's start today's tutorial. um, yeah, so let me check. Okay, this here. So let me start today's tutorial. Now I will, in this tutorial, I will solve some previous year assignment which was given at the end of the lecture 3. So the first question, let me insert the first question. Okay, question number 1. Yeah, so that's that. Draw. Okay, so I will start this today's tutorial by saying few words about the Legendre transformation. And the first question is about what is about the Legendre transform, and in this question it is asked the Legendre transform of the Lagrangian of a classical mechanical system. So at first let's see what Legendre transform mean. Now suppose you have a variable fx and suppose a variable fx and which is a function of x obviously, and it varies something like that. You draw a curve, it is something like that. Now if you to describe this curve, you can describe this curve by two ways. One way is you just mention each and every point in this space and what is the corresponding value of y and x. That means you just mentioning all the values in the curve. That is one way to describe is, one way of description is just mentioning all the value of x and fx. So that is a one way of description. And there is another way of description, which is you just mention what is the if I draw a tangent to this point, what is the value of this tangent, what is the inclination of this tangent, this line draw, and what is the intercept, that means where it cuts to the y axis. So if you mention what is this value intercept, suppose this is y c y intercept, and you also mention what is the inclination, that means what is the inclination, then and it is another description of a curve. So another description is you actually mention, description is you mention the inclination. Suppose the inclination of this straight line is am and the intercept is yi. So by these two number, by these two information, you can also describe this curve. Now this description is called mathematically the Legendre transform. The Legendre transform, Legendre transformation of this curve. Now as we know that as we know from the class lecture 3 that the Legendre transform of the entropy versus, suppose this is entropy versus internal energy, is something like this curve. Now if you draw a tangent, suppose in this point, then the inclination will be del is del s del u constant, other things, other macroscopic variable are constant. We know that this is nothing but 1 over t. So, or you can say it is beta, and this intercept is nothing but f equal to, this intercept is nothing but, here the intercept yi is equal to beta f. F what? F is the free energy. Free energy means F is equal to u minus ts. So this is the another description of this internal energy versus entropy versus internal energy curve. So this, in this description, the description is, you will mention at every point the temperature, inverse of the temperature 1 by beta, and the free energy multiplied by beta. So these two description is called Legendre transform of this SU description. Now in the similar manner, in the question it is asked what is the Legendre transform of the classical Lagrangian, right? So we, as we all know, the Lagrangian is a function of q and q dot, and from the equation of motion we know that momentum is equal to del L del q dot. Okay, now if we draw a Lagrangian versus q dot curve, suppose it is this, it will look like this. Now if we, now the normal description is, we will mention L and q dot at every point. It is a normal description, so what will be its Legendre transform description? So its Legendre transform description, to as we know, the Legendre transform means we have to know this the inclination, that means del L del qi, which is p. Okay, and the intercept, let us calculate that intercept here. Suppose it is a line at this point, suppose this is L, and suppose this is L and this is H. Okay, and this is the intercept. So here, now from the Euclidean geometry we know that what will be if know that the L minus H will be the distance between these two, which is nothing but, it is nothing then, what is the distance between here and here? That will be 0 to q dot. So this distance is actually q dot into the inclination. What is the inclination? Inclination will be here del L del q dot. Okay, del L del q dot. Now you can see that this H is actually L minus q dot into del L del q dot. Yeah. Okay, del L del q dot. Now you can see that this, you actually, if from the classical mechanics, you actually know this quantity up to a negative sign, it is called the minus H is called Hamiltonian. Hamiltonian of the system. We know that this minus h is nothing but minus h equal to q dot, means p q dot minus l, or rather write it in this fashion. Okay, q dot del l del q dot. So this is the Hamiltonian of this, or Hamiltonian of that system. Now we know that this Hamiltonian is nothing but the Legendre transform. Legendre transformed Legendre transform description Legendre transform description of the system. So now, we have solved the first question, and the answer of this first question is the Legendre transform of Lagrangian of a classical mechanical system is the classical Hamiltonian. Now let's go towards the second question. Okay, let's go toward the second question. Answer question 2. Okay. So this is the second question. Okay. So now we will solve the question number 2. Imagine a gas that has a fixed total internal energy and a total volume, but particles can flow in and out of this system. The Legendre transform of the entropy function versus the total number of particles may be fixed. So here it is asked, there are two systems, one is a reservoir and one other thing is system. Now between this reservoir and system, only the particle, between the reservoir and the system, the only particle can go through. So now what will be the Legendre transform if it happens? Then what is the Legendre transform of the entropy function versus total number of particles? So for pedagogical purposes, I will start from the basic. From that we when these two system, reservoir and the system, actually allowed to exchange energy, what will be the Legendre transform form of this entropy? So let's see that. First we will see if the two systems are allowed to exchange energy between them, what is the Legendre transform form of the entropy. So to see that, first write that total number of microstate omega net, capital omega net, should be equal to all energy possible with volume fixed volume and number of particles. Okay. So this will be omega 1 function of U1 into omega 2 total energy of the system minus U1. So the total energy of the system is remain conserved. So the total energy means the energy of the reservoir plus the energy of the system are actually constant. So that's why I write it here that the energy of the reservoir is omega 2 E minus E1. So now this is the, now let me calculate what will be the maximum number for which values of energy this total number of microstate is maximum. That means we have to calculate the W net into del E1 at energy E1 such that E1 star such that it becomes 0. So if we calculate that, that means E1, so okay, so calculate it, omega 1 E1 del E1 omega 2 plus omega 1 del E1 omega 1 E1 into omega 2 E minus E1. So this will be 0. Now at the max, if at E1 equal to E star, this quantity is actually 0. That means this summation should be goes to 0. That means each and every term should goes to 0. Or since this is the energy where the system will go, that means the all other terms containing other than E1 will goes to 0. That means the maximum energy will corresponding to sigma E1 into delta E1 sigma 2 E minus E1 plus sigma 1 del E1 is a function of E1 sigma 2 E minus E1. Now let E minus E1 is equal to E2, then it will become minus sigma 1 E1, since we can write del E1 is equal to minus del E minus E1, which is equivalent to del of del E2. So that means minus del omega 2 del E2 plus omega 2 del omega del E1 is equal to 0. So that means we actually get a form that 1 by sigma 1 del E1 sigma 1 is equal to 1 by sigma 2 del sigma 2 del E2. Since this omega 1 is only depend on energy E1, this omega 2 only depend on energy E2, so that means these to hold this equality condition, these two quantities should be separately equal to some constant. Now here the physics comes. Now here the physics, up to this the mathematics is there. Now here the physics part comes. Now if we ask, since mathematics tells us that since this is only a function of E1 and this is only function of E2, then to hold the equality these two quantities should be a constant. Now we know from the physical for our physical experience that when these two quantity, when the energy exchange between these two systems stop, that is when that means as we know this the total number of microstate should always goes to the state where the total number of microstate actually larger, a maximum possible microstate. So our system is always reaches toward that state where it has a maximum number of microstate. So that means it will towards the equilibrium, and we know that when the equilibrium reaches, when this is actually equal to temperature. So these two constant should be nothing but the temperature. So that's how it comes. Now if we know that, now if we rewrite it as sigma net is equal to summation of E1 sigma 1. Now we will write sigma 1 as e to the power s1. So write it here, a to the power s1 into similarly sigma 2 e to the power s2, which is a function of total energy, minus E1, it's also function of E1. Now we know that the maximum contribution of the summation will come from the maximum value of this entropy, when the value will be maximum, when this macro state will be maximum. So we know that the macro state will be maximum at E1 equal to E star, where this relation holds, okay. So now if you write it here, that in this fashion, so now if we can expand, since the total energy of the reservoir is huge, the amount, the energy the system poses is very small relative to the total energy of the system. So that's why we can expand it in Taylor series with respect to this energy. So we can write it S2 into total energy minus E1 into del E S2 E at E1 star, right? Let me write it in this way. So this will be E2 and E minus E1, and E minus E1 is actually E2, and it is E1 star. So we only kept only the only up to this term. Now if we put it here, what we will get? If we put it here, what we will get? We will get summation of E1 e to the power s1 E1, and we know that, since we know that del omega del 2, we will take it here, so it will become del E2 ln omega 2 is at E1 star equal to E1 is at E1 star, so is equal to 1 by T. So that means we know this quantity, and since the maximum of this contribution of the sum will be this maximum value of S1, so that will become e to the power S2 E into e to the power S1 E1 minus E1 star. So this will be always star, so this is actually star. E star is nothing but E star, E2 star, actually E2 star is nothing but E star into E1 minus E1 star. E1 star, by this quantity we know that this is temperature. Now this will be e to the power S to E star into e to the power 1 by beta 1 by T S1 minus E1 star, e to the power S2 E star e to the power, this is actually beta. If we write it 1 by T as beta, so beta into T S1 minus E1 star. So now to express the entropy, since up to this we only express this function as an entropy. Now to express the total number of microstate or total entropy, we just express it in this fashion. Now this quantity is called the free energy, Helmholtz free energy. It's called Helmholtz free energy. So this is called Helmholtz free energy. Helmholtz free energy. Now this free energy T S1 minus E1 is called the Legendre transform of the entropy function. So now we know that how to come, means how we will come to the point where we can say that if the system and reservoir only allowed to exchange energy between them, then we will know the Legendre transform form of this entropy when we describe the entropy as a function of energy only. Now in the question, so it is asked that the gas has a fixed total internal energy and total volume energy. So total internal energy and volume does not change, but what is changing here is the total number of particles. So if we follow these steps, we will actually reach what is the Legendre transform description of this entropy when the system is allowed to change particle between them. So let's see that. So to sigma or sigma net should be function of sigma 1. Only particle can change, so particle of the system 1 and the particle in the reservoir is the total number of particle minus n1. Okay, now as we did in the previous case, here also we can write sigma 1 n1 as e to the power s1 function of n1 and sigma 2 n2 means n minus n1 as a function of e is 2 n minus n1. Now what is the equilibrium? When we will say that the system and reservoir is at equilibrium, when that system plus reservoir total system means system plus reservoir will reach that state where total microstate number, the sigma net, is maximum. Again from the as the same analogy from the previous question, previous things. So now here what will be the, when sigma net delta n1 equal to 0, then we will say the system plus reservoir reaches the equilibrium state. Okay, so now let's calculate what is the meaning of these things. So if we follow these steps, same step, we will reach to this argument 1 by n, we will reach in this step sigma 1 del sigma 1 n1 is equal to 1 by sigma 2 del sigma 2 del n2, where n2 is nothing but n2 is equal to n minus n1. So you can see that we have reached mathematically to this state. Now let's again ask what this mathematical identity or mathematical equation physically means. Physically, when we say that two systems which are allowed to exchange their particles in equilibrium state, we will say that if the chemical potential between this system and reservoir is become a constant, become same, then we actually say on average there will be no transition of particle from reservoir to system. So that means this should be a constant, and this value of this constant is mu by t, minus mu by t. So this is merely a convention, minus mu by t. So that's it, minus mu by t. Now we'll use these things at, obviously, at equilibrium. n1 start at equilibrium, okay. Now again, if we express sigma net as sigma, since sigma 1 n1 and to sigma 2 n minus n1, we can since the reservoir, the total number of particles in the reservoir is much larger than this n1, the number of particles in this system 1, so that means sigma 2 can be expressed in term can be expressed in Taylor series. So sigma 2 n minus n1 sigma 2, that is actually n2, n minus n1 means n2 by n2 at n2 star, which is the value of n2 star. n2 star is nothing but n minus n1 star. So we know that from this, that at n2 star this is actually nothing but minus mu by kt. So sigma 2, if we put this value here, you will get plus n1 mu t. So we can again express, let me write it in this way so it will be more convenient, is so okay, this is not actually s s, so this will be s, okay, s 2 to s2 s2, okay. This is actually e to the power s 1 n1 e to the power s2 n2, and you can see that not del omega 2 del n2 is actually that, actually del ln omega 2 del e del n2 at n2 star is equal to minus mu by t. So we have to write it here in terms of minus, okay, minus mu by theta. So that's that. So if we put it there, we will get e to the power s2 n2 e to the power s1 n1 e to the power s2, this will be sn, okay, this will be sn e to the power s2 a2 into e to the power s n1 mu by t. So again you can write it here as sn e to the power 1 by t, if I write it 1 by t t s1 n1 plus n1 mu, right. So this actually that means beta into t s1 n1 plus n1 mu, right. So this quantity written here is the Legendre transform, Legendre transformed form of the s1 n1 comma n1. That means in terms of Legendre transformation we can express s1 n1 n1 in terms of inverse of temperature beta and this quantity beta t s1 plus n1. So this is actually answer, this is the form of the Legendre transform form of the entropy. If we kept fixed, if we only allow system and reservoir to exchange particle between them and other things kept constant, so that means the answer will be s minus s, actually s plus mu beta n. So okay, if we put it back here, so beta means S1 plus mu, okay, mu S1 plus beta mu N1. So that means this actually answer. So you can see from here, if we if we take beta, so it will become Ts plus mu n. So that is the answer. So we have solved the question 2. Now I will again mention another thing now similar to these two. And now if one asks you that suppose there are a system there are a system and reservoir where they can only exchange their volume, right? They can only exchange their volume and all the other things kept fixed. That means E1 kept fixed, N1 kept fixed, only the volume is changing. Now as we have grow our as we grow our intuition from these two calculation, now we can apply our intuition here to tell what will be the Legendre transform form of this S V1 comma V1. So obviously one will be beta and other will be what? It should S beta into S V, right? Beta into S minus P V. How I P V1, right? P V1 S1 P V1. How I can write it? Because I know that del S del V1 with fixed energy or temperature and total number of particle, it will be at equilibrium. That means at V1 star the pressure of the two system will be equal and P by T is so this will become P by T. Now we can see from these two problems, it is straightforward that here it will come minus P into V by T. So if I T common, so this is the energy, this is this is the Legendre transform form of the entropy and this total description entropy, that means V1 and comma V1. So you can write this the description either in terms of H1 V1 comma V1 or in terms of temperature and P V1. So that's that. Now one thing is that you should always keep in your mind that why do we need this Legendre transform. So this is a good this is actually one thing. So why we need such description? If you can describe a curve in both these two terms, so why should you need another description? Now here the interesting part comes. Now you can see from here anywhere, suppose that here also. Now here you can see that to describe the curve you need two extensive quantity, right? This is also extensive quantity, this is also an extensive quantity. Now you want to describe your system in terms of, means if you add something in your system and your description you have to again change your description, that is very worst situation. Now you want to go toward a description system where you at least have a intensive quantity. That means if you change the system by adding similar system to the system, the things will not, quality will be changed. That means in the Legendre transform, in your back of the calculation, we always want to describe the system, or we reduce the extensive quantity to a intensive quantity, means so that we can express the system not in terms of this extensive quantity but in terms of intensive quantity. So here that is come that here actually you can see that here you get one intensive quantity, another intensive quantity, so you reduce the system from system description from two extensive quantities to only one extensive quantity and one intensive quantity. Similar is here also. So one is beta and another is thing, and similar also for the energy. So that is why you need, or you actually want to Legendre transform your extensive quantity to reach towards a intensive quantity. So that's that. Now we have solved this question 2. Now we will go toward question 3. Okay, let's move toward question 3. Question 3. Okay, question 3. Question 3. Insert. Now this is a very tricky question. Now you should actually give some attention to this question and how we can solve this question very easily, because this question is actually very tricky question. So this question actually this type of question is very important for your competitive exam such as JEST like things. So this is the question. It is asked here that imagine a quantum gas of non-relativistic particles in 3 dimensions. Okay, if the energy per particle is expressible as U equal to 3 by 2t plus t square by t0, where t0 is a constant independent of all properties of the ideal gas with dimensions of temperature, the formula for the pressure versus temperature and density of the particle. So you have to solve this question, right? Now to solve this question, let us know what relation actually follows by the energy of the particle and the pressure of this gas particle. So to do so let me see. It's a very basic calculation. So okay, so I will straightforwardly write. It is not actually straightforward, so I will write the expression for we know the 3 type of gas is there. One is ideal classical gas. Second is fermions. Third is bosons, right? So you can write the energy per volume, that means total internal energy per volume, energy density, as integration d cube r by C0 cube beta r square e to the power r square e to the power minus beta mu plus q. Now if q equal to 1, q equal to 0, it is classical gas, and Q equal to +1, it is fermions. Q equal to -1, it is bosons. Okay, now similarly you can write the expression for the number of particles per volume, which is actually TQR by C0 cube 1 by ER square e to the power minus beta mu plus Q, where C0 is called thermal wavelength, which is 2 beta pi square h cut square by m to the power half. This is called thermal wavelength. Now one thing is has to be noted here, this is crucial, that these two expression only valid, these two expression is only valid for gases, for non-relativistic gases, non-relativistic gases, that means whose energy momentum relation will be p square by 2m, and this is the energy and the density, energy density and the particle number density only for gases which is in 3D. So for these two are valid only for the energy when the energy is parabolic to the momentum, that is E equal to p square by 2m, that is actually non-relativistic gases and in the 3D, and your spatial space is 3D. The particle is moved in 3D space, that's it. So then these two relations are valid. Then from a tedious calculation, which is not important, means you don't have to do it by yourself, you only have to know that things, that the rho is equal to the energy particle density is equal to minus m by beta h cut square to the power 3 by 2 Li 3 by 2 minus Qz by 2 root 2 pi to the power 3 by 2 into Q. Okay, and these two only valid. Okay, let me finish it. Only valid minus m by beta h cut square to the power 3 by 2 3 Li 5 by 2 minus Qz by 4 root 2 pi to the power 3 by 2 Q beta. So these two only valid for Q equal to 1 or plus 1 or minus 1, because if you put Q equal to 0, this so you have to take in special care when Q equal to 0. And these Li functions are nothing but, it is called polylog function, and Li s z is nothing but z plus z square by 2 to the power s plus z cube into 3 to the power s plus dot dot dot, this like this is polylog. And similarly you can calculate the pressure of the system will be minus Q by C0 Q beta into dq r log of 1 plus Q e to the power minus r square e to the power beta mu. So again, for q equal to 0, you have to you have to do separately for q equal to 0. Guys, for q equal to plus minus 1, it is valid. So now again, from the similar kind of calculation, you actually get the result q pi to the power 3 by 2 beta h cut square pi square by m to the power 3 by 2 into beta li 5 by 2. Now the interesting thing is, when you just divide the q by uv, that means p by uv, it's actually always p by uv. You can see from here that p by uv is actually 2 by 3 for q equal to plus minus 1. So it does not matter what type of gas it is it statistically follow the rule of fermions, or the rules of bosons. It doesn't matter. The p by uv always follow this rule. P by uv always equal to 2/3, and it's only true as we know that for non-relativistic gas particles move in 3D. Now just quick check for this for q equal to 0. As we know that for q, we know that for classical ideal gas, P is equal to PV is equal to NT, as K beta is equal to 1, and we know that U is 2/3. Okay, N equal to, sorry, for 3D. For 3D, we know that 3 by 2 NT, again KB is equal to 1. So that means PV by U is nothing but 2/3. That means P by UV is 2/3. So that means for Q equal to 0 also, P by UV is actually 2/3. So you see from here that whatever the value of Q is, that means whatever the nature of the gas is, that means is it classically behave, or is it behave as a fermion, or the gas particles behave as a bosons, it doesn't matter. As long as the gas particles follows the energy momentum relation as like this, p square by 2m, and it moves in 3D, then the pressure and the internal energy per unit volume will always follow this relation. So now if you just notice that here it is asked that in 3D a quantum gas of non-relativistic particle in 3 dimension. Now if that question is there, anyway it seems quantum gas and non-relativistic words are there. So whatever the gas is it quantum mechanical gas or classical gas, it doesn't matter. As it is non-relativistic particle, that means it follows the parabolic relation, that's it. So then we know that the PVP, so that means we know that what is the state of the equation. P should be 2/3 UV minus UV is equal to UV means U by V, that means UV, that means PV should equal to 2/3 U. 230. This is the state equation. Now it is straightforward. Just put the value of U here, I will get the result. So U is nothing but 3 by 2T plus T square by T0. Okay, let put it there. So it will be that PV is equal to 2/3. Okay, this is the particle per this is energy per particle. So and here it is the energy of the internal energy of all molecules. So 2/3 into small, this is small u. So total u will be this into total number of particles. So into 3/2T plus T square by T0, which is NT plus 2/3 N T square by T0. Now you see that this is the answer of this question. So the formula for the pressure versus temperature and density of the particle is this. So P density will be N by V, that means N by V T plus 2/3 N by V T square by T0. So this is rho T plus 2/3 rho T square by T0. So P, pressure of the system, the thermodynamic relation between pressure and the density and temperature is this. So you can see that it is very easy if you know that in 3D for non-relativistic particle it's always follow PV equal to 2/3 U, and then you can always calculate the state equation of the system, which is actually P equal to rho T plus 2/3 rho T square by T0. So that's it. So we have solved the question 3. Now let's move toward the question 4. Okay. Question 4. Yes, no, question 4. So question 4. So now here the question 4. Okay. So in question 4 it is asked that for a gas of non-relativistic fermions in 3 dimension, the leading contribution to the entropy at high temperatures may be leading contribution to the entropy at high temperature. So it's a very tedious calculation, so we will calculate it here. So let's do it. So from the so as we write the previous expression, so what things we needed here? So we have to expand since internal energy. So internal energy per volume, we have to expand these in terms of when we have to need this we have to calculate the value of UV, and we also need to calculate the particle density rho. So these two things we need here. So let's calculate first UV. So we know UV is equal to nothing but UV is equal to integration dqr. No, let me write it in the simplest form so that way you can, no, let me introduce a thing from which you can, so we will calculate this quantity only, g n q, which is integration dq r to the power n by e r square z inverse plus q. Now you can see from here that uv is nothing but this quantity by c0q into beta, right? This is uv is actually g1 q by c0q into beta. Okay, let me check it. So this is this, and rho is only dqr by c0. This is only z0q by c0q. So if we can write the contribution of the entropy at high temperature of this quantity, we can also then write the contribution of the high temperature in uv. So let's write that. So what happens in the high temperature, let's see that. At high temperature, Z is nothing but e to the power beta u. Beta mu is the chemical potential. Now at high temperature, Z will be e to the power mu by T. At high temperature, this quantity will be very less, because as T goes to infinity, this term will be very small, right? So that means we can express, okay, so this is very small. When t goes to, t is a very large number, so this quantity is very small. So now we can expand in terms of this quantity. So to do so, let's do it. Integration dqr r to the power 2n into, if I just multiply z e to the power minus r square in both sides, it will become 1 plus q e to the power minus r square into z. Now you can write dqr as 4 pi r square dr. So we'll write that. So 4 pi dr, r square will then become r 2n plus 1 z e to the power minus r square 1 plus q e to the power minus r square z to the power minus 1. Now we'll expand, since z is very small, and this term will also very small if t becomes very high. So we can expand this in terms of z, and we only kept up to second order, up to second order. Okay, so if we express it here like this, so it will become, what it will become. So if we expand in Taylor series, what it will become, 1 minus q e to the power minus z. Let me write it in this way, z q e to the power minus r square. Okay. I only kept only these two terms. I will not go further, I only kept these two terms. Okay, so then this integration, because I only need the leading order contribution, right? So all the other will be higher power in z, and that will contribute less because z is less than 1, so it will contribute less. So that's why we will not expand it more. So 4 pi dr r 2n plus 1, this is z is there, so first term will be to the power minus r, this is approximately equal to, second term will be minus, yeah, so minus 4 minus, this will be minus integration dr r to the power 2n plus 1 q z e to the power minus 2 r square, right? So let's first calculate these things. So this is nothing but this integration 0 to infinity, this integrating 0 to infinity. So we know that 0 to infinity dr r to the power 2n plus 1 e to the power minus r square is nothing but half of gamma 2m minus 1 equal to 2n plus 2, that means m is equal to 2n plus 3 by 2. So that means gamma 2n plus 3 by 2. Now we will calculate this term. So this term will become minus qz plus qz equal to 0 to infinity dr r to the power 2n plus 1 e to the power minus 2r square. Now if we take alpha is equal to root 2r, that means d alpha will become root 2r and r to the power 2n plus 1 will become so d alpha root 2r, okay, and r to the power 2n will become so this will become alpha by root 2 to the power 2n plus 1, so that is 1 by 2 to the power n plus 1 alpha to the power 2n plus 1, and so that's it. So that means we can write it here in this in terms of alpha 0 to infinity d alpha by root 2 1 by 2 to the power n plus 1 alpha to the power 2n plus 1 e to the power minus alpha square. So that means qz by 2 to the power n plus 3 by 2 into this again 0 to infinity d alpha to the power 2n plus 1 0 minus alpha square. Now you can see that this and this is actually exactly same, so this will be half gamma 2n plus 3 by 2, actually 2n okay, so this will be 2n plus 3 by 2, that means actually n plus 3 by 2. So it's nothing, I actually write is equal to n plus 3 by 2, nothing, I write it so in this form. So this will be z 2 to the power n plus 3 by 2 into gamma half, simple. So this will be gamma n plus 3 by 2 by 2. Now if we put these two things here, we'll get is 4 pi z, so this become only 2. And if we since these two integration contains this gamma n 3 by 2, we can common it, gamma 3n plus 3 by 2, gamma n 3 by 2. And what other things remains is first term. In the first term there is no other term is remain, so it is actually 1. And in the second term only remaining thing is qz by 2 to the power n plus 3 by 2. So let me check it, is it correct? 2 pi z gamma n plus 3 by 2, 1 minus qz by 2 to the power n plus 3, right? So similarly, in the similar manner, I don't know, it's the not similar manner. So since we calculate g and q, now we can easily say what is the value of ub and rho b. So let's calculate that. So let's write that uv is nothing but z 1q by c0q into beta. What is g1q? g1q will be, if we put 1 in place of n, so it will become z, since this is the expression for g and q. So if we put n equal to 1, so we'll get 2 pi z gamma 5 by 2 1 minus qz by 2 to the power 5 by 2 pi c0q beta. And what is the value of rho? That will be z key by c0, so that is 2 pi z gamma 3 by 2 1 minus qz by 2 to the power 3 by 2 pi c0q. Now up to that we have right. Now what is that? Entropy, right? So this is the thing we need. What we need? The entropy. Now we know that entropy is TdS is equal to internal energy plus PV minus mu n, right? So we have already calculated the leading order correction of U and rho, that means n. And actually we know that, since we know that PV is actually 2/3 U, so we also know the leading order correction of PV also. So let's, and we actually don't know the value of mu. So to calculate the value of mu, we want to calculate the value of mu from here. So we will calculate the value of mu from here. So first write it, what is the leading order correction of this so we want to write U, since this actually contains so many things, this constant, so we want to get rid of this constant. So we want to express U by n, actually uv means U by v by rho is uv by rho, which is actually U by v by n by v, so that means U by n. We can write it like that. So if we divide these two things, so many things will be cancelled out, so we will left things which will be, so U by v, so this term does not contribute, c0 cancelled, and 1 by beta will be there, and 1 gamma 5 by 2, gamma 5 by 2 by gamma 3 by 2 will be there, and first term is 1 minus qz by 2 to the power 5 by 2 by 1 minus qz 2 to the power 3 by 2. So gamma 5 by 2, since we know that gamma n plus 1 is equal to n gamma n, so that means gamma 5 by 2 is equal to gamma 3 by 2 plus 1, which is actually 3 by 2 gamma 3 by 2. So that means gamma 5 by 2 by gamma 3 by 2 is equal to 3 by 2. So that means 1 by beta into 3 by 2. So now we only kept, since z is small, so we can do, we take it up, 1 minus qz by 2 to the power 3 by 2 minus 1. So since z is very small, so we can expand in Taylor series and only keep the first order. We will get 3 by 2 beta 1 minus qz 1 by 2 to the power 5 by 2 minus 1 by 2 to the power 3 by 2, right? Okay, so what we'll get, 3 by 2 beta plus 3 qz. Okay, have I done something wrong here? Is it really minus qz? Okay, no problem. qz by beta 2 to the power 5 by 2 is 2 to the power 5 by 2 is nothing but 4 root 2, so that means 8. So that's it. So that is my u by n. So u by n, now we can simply, now okay, u by n, so now what is the value of pv now? U by n is that, so we know that pv will be 3 by 2/3 u, so that means 2/3 u, which will be 2/3 u will be n into this, so that means u/3 2/3 u by n, we know that, so that n into u by n, that means 2/3 into n into 3 by 2 beta plus 3 qz by 8 beta root 2, so that means 3n by 2 beta plus qz by 4 beta root 2. So that's it, pv is equal to that. So we know already u, v, and we actually want to know what is the value of z. So to know the value of z, we will use the expression uv. So since we know that u by v is equal to 2 pi z into gamma 5 by 2 c0q into beta, c0q into beta. So we only kept up to order this to invert this relation and get the z in terms of u by v. So we only want to do that. So to doing so, we need, since in this equation there is no beta is sitting here, so we have to also inverse the relation of beta. So for that purpose we take the value of beta is equal to u by n. So we only take the value of beta 1 by beta. So we only to express beta in terms of u, we only take up to the first order. So if we take this first order only, so what is the value then? So u by n equal to, 3 by 2 beta. So we know that u by 1 by beta is equal to 2/3 u by n. So we'll use that here. So beta in place of beta, if we write 1 by beta, u 2/3 okay, is it 2/3? Yeah, it is 2/3 or 3 by 2. Okay, 2/3. Okay, let me check it. It is 2/3 or 3 by 2. It is 2/3. N2 is 2/3 u by n into z, into 5 by 2 means 3 by 2 is gamma 3 by 2 by c0 cube. So 3 by 2 u. So this is 1 by v, 1 by, sorry, is actually 1 by v. So this is nothing but, sorry, n by v is equal to z. What I left is gamma 3 by 2, gamma 3 by 2 again half into gamma half, which is actually root pi, right, root pi, and c0 cube. We know that beta h cut square pi square, beta h cut square pi square, beta h cut square pi square 2 beta h square by m. So these we know. C0 means that, okay, C0 means that. So in place of beta, again put this value. So this will be, beta means 3 by 2 n by u. So 3 by 2 means 3 n h cut square pi square by m to the power half. So this third up root pi by c0 q means 3 . Okay, 1 2 pi z is missing here. 1 2 pi z should be there. 1 2 pi z should be there. Okay, so I have missed this 2 pi z somewhere. 2 pi z should be there. So 2 pi should be there. So 2 pi, here there is a 2 pi sitting there into 2 pi. So 3n h cut square pi square by m u to the power 3 by 2. So this cancel out. So 3 by 2 and 1 pi 3 by 2 is out. So you will left with n by v is z by 3n h cut square pi u m 3 by 2. You can express z as n by v into 3n h cut square pi by u m to the power 3 by 2. So that means we know e to the power beta mu is n by v 3n h cut square pi u m 3 by 2. That means mu will be 1 by beta log in natural base n by v into 3n h cut square pi u m to the power 3 by 2. So now we have expressed mu in terms of this. Now we can actually ready to express the leading order contribution of the entropy. So the first term will be Ts will be simply u plus pv minus mu n. So u plus pv, I only take since log of this term, since okay, so this u plus v, okay, u plus v, yeah, u by n is 3 by 2 beta. So I will not include this term z, because this is I will not include this term. I only include this term only. Okay, if I include that also, so that will be 4 3. Okay, if I include this term also, so it will become 2 root 2. Okay, let me write it like that, so then it will clear. Z, okay, z means this. Okay, I will only take first part from the u and the first part from the pv. So what it will become, u plus pv. So u, what is the value of u here? First u is u by n. U by n is equal to 3 by 2 beta. That means u equal to 3n by 2 beta. So let me write it there, 3n by 2 beta plus value of pv. First 3. It should not be 3. So it's 2/3 into 2/3. It should be n by. So it should be n by beta 3. So n by beta, the first part actually n by beta, and the mu n. So we already calculated the value of mu, so we'll put it here. So it is nothing but mu, value of mu will be 1 by beta ln n by v into 3n h cut square pi u m to the power 3 by 2. Okay, this is mu and there is a 1 n. So that means S will be, T is actually 1 by beta. So T is actually 1 by beta. So 1 by beta, 1 by cancel out. So S will be, if I take common V, so that will be 3 by 2 plus 1 is 5, then n by v is rho, minus there will be a rho, and this is actually rho, ln rho into 3 n h cut square pi u m to the power 3 by 2. So that is my answer. So let's check what answer is correct here. So 5 by 2 rho ln 3 n h square pi m. You can see here that this a square, aq will cancel, so this actually doesn't matter. So that means 3 v 5 by 2 rho minus rho ln minus rho. Okay, let it where it is minus ln rho. So this sign actually wrong here, it should be minus here, so it is a fermion, so it should be negative here, so negative sign should be there. Rho ln n by v, that means rho 3n h cut square pi square 3n h cut square pi by um. So that means this is the answer of this question. This is the answer of this question. That means the leading order correction to the entropy is this. So that means we have all solved the question number 5. Then let's go move to the next question, and that is the question number 6. So let's solve that question. So let me insert that question first. So this is the question. Okay. Yeah. So this is my question. Now it is asked the temperature at which the condensate fraction becomes 0.5 for non-relativistic Bose gas in 3 dimensions. So as we know, for Bose gas, the total number of particles is actually summation over the average number of particles present at state psi, and we know that this I is 1 by e to the power beta psi, my e to the power beta psi z inverse minus 1, and z inverse is nothing but e to the power beta, which is vagacity, e to the power beta mu. Now you can check from here, since when we just replace this summation signs by integration signs, we write a thing d epsilon, or in d epsilon in terms of 4 pi p square dp, right? So when we write this summation as an integration 4 pi p square dp, then the contribution from p equal to 0, you can check from here, is actually 0. That means the particle which remain in the p equal to 0, actually we are not taking into account the particles which are at p equal to 0, or actually momentum whose momentum is 0. So that means we have to take into account this state, since in case of fermions this is not a thing to worry, because in case of fermion we already know that in a single state no two particle can remain. That means only from a huge particle, for only one particle can remain there from a huge particles set. So that means that the contribution is negligible. So that's why in case of fermion it's nothing to worry. But here, since in the bosons in a single state so many particles can be stay together, so it's a so you have to consider the number of particles which are there in ground state, that means epsilon equal to 0. So let's check what is the number that's remain there. So this will be, suppose this here, from here is straightforward to check, n0 will be, if I put z equal to 0, that means we put epsilon equal to 0, then it will be 1 by z inverse minus 1 is equal to z by z inverse 1. But since we don't know the z, so to write n0 in terms of this will give no information, because we want to know the what fraction of the total number of particles at temperature T will stay at ground state. So we want to know the value of n0 in terms of n and temperature T. So let's do that. So as from our previous as I have told you in the question number 3, that n or rho can be written in terms of 1 by v by c0 cube into some poly log function li rho will be, let me check it, rho will be C0q by V is polylog of Z. So let me write it like this, G3 by 2 into Z. Z is the phagastic constant. Now the thing is, this the maximum value, this is a function of t, so t is actually rho, then rho means there is 1 by C0q, and if I put it like this, n equal to total volume by C0q t into G3 by 2 Z. Now the thing is here, one interesting thing, that the value of G3 by 2 in range when Z is in between 0 to 1, then there is a maximum of this function G3 by 2, Z3 by 2Z always less than Z3 by 2 at the value Z equal to 1. So in the range Z equal to 0 to 1, this function is monotonically increasing, and at Z equal to 1, this function has a maximum. This function, there will be a ground state contribution, so this will be n0, so these terms will be maximum at Z equal to 1. Now suppose that n minus n0, okay, let me write it in this way, C0q a function of t, Z3 by 2Z. Now suppose if in your system there is particle, suppose the particle which is at temperature T which is greater than this number. Suppose that you in a gas you want to put in a volume view, you want to put n number of bosons which is actually greater than Ne. But think it, the value of G3 by 2Z, its maximum value is G3 by 2Z equal to 1. That means the maximum number of particles at any temperature that the excited state the particle will remain at the excited state will be bounded by this number. That means maximally at temperature T, that much number can be present in the excited state. So what about the other particles? Because you want to put the total n number of particles in volume V, but actually your mathematics tells you that only this much number of particle can stay maximally in your excited state. So what about the other particle? So obviously the other particle should sit in the ground state. So that means the other particle, that means n minus any number of particle should be sit at the ground state. Ground state at temperature T. Note, at temperature T maximally this is the number of particle that could stay at excited energy. Excited energy means epsilon not equal to 0. Now if we, since we can control the temperature, now if we decrease the temperature at T equal to Tc, suppose that we decrease the temperature and at T equal to Tc Z become 1. Now if Z become 1, let's take a look on this expression n0, where n0, let me write it here, n0 is actually Z by Z minus 1. So if we see it that at Z equal to 1, at t equal to tc, z equal to 1, what the n0 will become? N0 will become infinity. If we put z equal to 1, that means n0 will become infinity. That means at z equal to 0, all particles should go at the ground state. That's it. Otherwise, since this is the contribution will be maximum, or all the contribution will come from this n0 term, this n0 term, which is actually at z equal to 1. At z equal to 1, n0 infinity. So this term will not contribute. So at t equal to tc, at t equal to tc, all the particles LC will come to the ground state. So what will be the value of n then? The value of n will be v by C0q to Tc and to Z3 by 2 at z equal to 1. Now so this is the total number of particle. So this will not change with time. So this will be the total number of particle always. Now let's now what's some glitch is there. So now so this will be the thing. Now let's see what is the value of n e by n, right? N e by n. Let's see that n e by n will be, so n e is v by C0q at t, g3 by 2 z equal to 1, and v by C0q tc at z3 by 2 z equal to 1. So all the term will be cancelled, only remaining term will be C0q tc by C0q t. So let me check it here. So that means it will become, since we know that C0 is proportional to 1 by root t, so that means it will become t by tc to the power 3 by 2. Now we can calculate this much amount of particle at temperature T will remain at any temperature in the excited state. So how many of them will remain at N0 at ground state? N0 will be at temperature T. At temperature T will be N minus Ne by n. So that much out of total n particle, let me write it, out of total n particle, okay, out of total n particle, any number of particle is there in the excited state at temperature T. So that means the number of particle which will be there in the ground state will be that. So if I n0 t divided by n with both sides, so we'll get 1 minus net by n, so which is nothing but 1 minus t minus tc to the power 3 by 2. So that means at time t at temperature T, so that is the fraction of the particle that will be there in this ground state, 1 minus t by tc to the power 3 by 2. Now let's see the question. In the question it is asked that at temperature, the temperature at which the condensed state fraction becomes 0.5 for a non-relativistic Bose gas. So condensed state means when in the momentum space the all particle will freeze. That means the all particle will in the momentum, the all particles will be in a same position, p equal to 0 in the particles in the momentum space. So that's what is the n when it is asked that when it will become 0.5 the fraction. So let's check. This means this is 0.5, that means 1 minus t by tc to the power 3 by 2. So that means T by Tc to the power 3 by 2 is actually 1 minus 0.5 will remain 0.5. So T will be Tc into 0.5 to the power 2/3, and if we calculate it, we will get, if you use your calculator to calculate, you will get the value will be 0.6 Tc into actually this is the answer, 0.06299, 0.06299. so that will be the temperature when the number of particles that will be there in the ground state is exactly half fraction of particle will be there in the ground state, that is actually T equal to Tc 0.6629. so that's that. So that is the last question I actually solve in this, I have planned to solve in this tutorial. So okay, someone is there. Okay. So that is that. So now hence no one is present there, so I will end my meeting here. So that's it.